This is our first lesson in multivariable calculus, and in it we will look at the Cartesian coordinate system. Now, this is named after René Descartes, a 17th century French mathematician. I don't normally cover Cartesian coordinate systems this early because I hate to put Descartes before the horse, but sometimes you just have to. Up to this point in your calculus career, you are familiar with a two-dimensional coordinate system consisting of a flat plane of x and y. All of your calculus functions were y as subfunction of x, where you plotted points in the two-dimensional plane and you used those points to define functions. You took their derivatives to find slope. You found the area under curves. And this 2D plane was adequate for everything that you needed to do. Of course, these points had an address, A, B, which would represent how far across in the x direction they were and how far up in the y direction they were. Of course, we're going to have to use a three-dimensional coordinate system for multivariable calculus. It's right there in the name, multivariable. We're going to need more than just y as a function of x. Sometimes we're going to need z as a function of x and y, in which case, at minimum, we need 3 dimensions. Here's that three-dimensional coordinate axis. It's going to consist of an x, a y, and a z axis. And you kind of have to get used to this configuration. It's fairly standardized that the x-axis is portrayed as coming out of the board at us, and the yz plane is the flat plane that we're used to seeing as the xy. Locating points here is a little more difficult. After all, we don't have sort of the opportunity to look straight down on the plane because this is a three-dimensional space. It actually has depth as well as planar projections. So let me place a point in it, and then we'll talk about where that point is actually located. So this will be point P. Now, one of the difficult things about a flat representation of a three-dimensional space is that added dimension of depth is something we really have to work in our mind. There's various technology tools that will help you to graph these on a computer so you can turn and rotate them. But one of the things you have to develop is sort of the skill of being able to visualize 3 dimensions in a flat plane. To do so, we're going to sort of trace out along the x direction for how far forward point P is above the zy plane. I'll call that distance A. So that'll be the first coordinate of point P. And then we'll trace across in the y direction, and that will be the second coordinate B, and of course it represents how far point P is from the zx plane. And then finally, we'll run a vertical line straight up parallel to the z-axis. I'll call that distance C, and this is how far above point P is, how far above the xy plane it is. So there's the location of it in 3D space. Now, we got used to finding the distance between points on a 2D coordinate axis. In this case, I'm going to find the distance between the origin and point P. So the origin, of course, will be at 0, 0. And to do that, of course, we use the distance formula, which is based on the Pythagorean theorem. So that distance here, the distance to point P, so maybe I'll give this origin an address of P naught. So the distance P naught P squared was equal to, well, how far across we went, which was a minus 0 squared, and how far up we went, and that's going to be b minus 0 squared. Of course, if point P naught were some other location, then we would plug in its address for these zeros, and there it is, the Pythagorean theorem adapted to be the distance formula. I can take the square root of each side, and that would give me the distance P naught. Well, we'd like to develop the same sort of thing, a three-dimensional analog to the distance formula. Now, of course, this was easy to visualize just because we can easily see the right triangle that's inherently sitting right here. We know that forms a right angle, and the two legs are a minus 0 and b minus 0, so it made sense that that hypotenuse simply used the Pythagorean theorem. Well, here in the 3D space, we kind of lose that opportunity. And the main reason we do is there's no such thing as a right triangle that has 3 legs. I can still draw and visualize the distance between the origin and point P. And once again, I'll call the origin point P naught, and of course it has an address of 0, 0, 0. My point P up here has an address of A, B, C. So the question is, how do I form a distance formula to determine that distance in this 3-dimensional realm? Well, what I'm going to do is draw in an auxiliary line to help us. And that line is going to go right here. And here's how that's going to help us. We know that the distance A and B are perpendicular to each other because they represent distances along the x and the y axis. So this is a right angle. That means this auxiliary line I've drawn in, that's actually the hypotenuse of a right triangle that lies entirely within the xy plane. Temporarily, I'll call that distance d. So we can use the Pythagorean theorem on these 3 numbers. D squared equals a squared plus b squared. Well, d also lies within this triangle. It not only lies in the xy plane, but the distance c running parallel to the z-axis is actually perpendicular to that length d. So it meets right here as a right angle. And that makes the distance we're after, that is P naught, that makes that the hypotenuse of that right triangle with d and c as its 2 sides. So I can write that P naught squared is equal to d squared plus c squared. And of course, you can see now that I can substitute this d squared into this one. And we end up with something that I like to call the hyper-Pythagorean theorem. P naught squared is equal to a squared plus b squared plus c squared. And of course, just like we did over here, P naught did not have to be located at the origin. It could be any other point in 3D space, in which case this formula would read P naught squared equals a minus that x coordinate of P naught, b minus that y coordinate of P naught, and c minus that z coordinate of P naught. So the distance formula translates really well into 3 dimensions. And that brings up another point. Because we have the distance formula in 2 and 3 dimensions, but it's in terms of 2 specific points, let's imagine what would happen if we made P a general point. So in 2-dimensional space, I've got a set of points P located at x, y, and they're all the same distance from a fixed point. I'll call that P naught. Well, we know what this is. This is a circle, and the fixed distance is the radius. Well, if P naught is at a specific address, in this case, let's put it at point AB just to give it an address, then xy is the set of all points that are equidistant from AB, and that distance is r. And of course, we know what this formula is. R squared equals x minus a squared plus y minus b squared. And that's the formula for a circle. It's a circle of radius r, whose center is AB. So radius equals r, and center is AB. Well, in the same way, we can adapt this hyper-distance formula, this hyper-Pythagorean theorem for 3 dimensions, except, of course, it won't form a circle. A 3-dimensional circle is better known as a sphere. So if we have a sphere, it's the set of all points equidistant from a fixed point, but in space. So all points x, y, z that share the property that they are a fixed distance r from point P naught would then have the following formula. Let's give P naught an address. I'll just keep using A, B, and C out of convenience. And of course, that means we'll end up with a formula for this 3D sphere of r squared equals x minus a squared plus y minus b squared plus z minus c squared. And of course, this would be a sphere with radius r and center of A, B, C. Okay, that's all for now. Hopefully you feel more comfortable with the Cartesian coordinate system in 3 dimensions and the formula for our first 3D curve, the sphere. It won't be the last multi-dimensional formula that we'll be looking at this semester.